This is Regents Review Unit 9, and our focus is on solutions. When we talk about a substance boiling, we have to talk about the attractive forces, those intermolecular forces. So boiling occurs when we have enough heat energy to overcome those attractive forces between molecules. So the stronger those attraction, the stronger the intermolecular forces of attraction between these particles, the higher the boiling point, because it takes more energy to break those attractions. And therefore, the weaker the intermolecular forces, the lower the boiling point. Reference table H shows us the vapor pressure of 4 liquids. And from this, we can get the boiling points of these substances. So the dotted line represents standard pressure, which is the 101.3 kilopascals, or 1 atmosphere, going from table A, our standards. And so if we go across at standard pressure, we see that water boils at 100 degrees Celsius. And if we change that pressure, that vapor pressure, then we change the boiling point. So an example of a question would be, what is the boiling point of ethanol at 50 kilopascals? So I locate ethanol, which is this curve here. I'm going to 50 kilopascals, and I go down, and I see that this is going to occur or boil at, if we have 50 here, we have 55, we have 60, so at 60 Celsius. It's important to note that the scale on the bottom goes by 5s, but the vertical scale here goes by 10s. So just be careful if they're asking you about vapor pressure versus temperature, that you're reading the scale correctly. In terms of making a solution, we have a homogeneous mixture is a result of taking a solute, our dissolved substance, and putting into, in this case, water, our solvent. So an example, if we take sodium chloride, our solid, and put it in our solvent water, we form NaCl aqueous, which means it's a homogeneous mixture. It's uniformly distributed or dissolved. We could separate that physically by either evaporation or boiling. And you can see here that when we dissolve our ionic compound, our salt, that it's going to separate into ions. And since these ions have charges, in this case Na plus and Cl minus, these moving charges or these moving ions allow for the conduction of electricity. So we say that things that are going to break apart into ions like salts, acids, and bases are going to be electrolytes. They conduct electricity. Table F was our table of solubility to determine if a substance will dissolve or not. Is it soluble or insoluble? So if the substance is soluble, so in the soluble column, that means it dissolves in water, and the insoluble column means it does not dissolve in water. We call this the formation of a precipitate, a solid that is coming out of solution. The exception column negates that. So for example, if I have a substance and it is soluble, so let's say I have AgNO3 and PbCl2. So I place these aqueous solutions together. If the reaction takes place, we form a double replacement where Pb goes to NO3 and Ag goes to Cl2. Then I produce these two new compounds, and I want to determine which one is going to dissolve and form an aqueous solution, if any, and which one is going to form the solid precipitate. So that one's going to be insoluble. So let's look at this one first. I'll look at NO3. I find nitrates. It is soluble. There are no exceptions, so this is going to dissolve. And so this would be an aqueous solution. So we can put AQ next to it. And then I'm going to look up the Cl, and I find Cl minus under my soluble column. But there's an exception. Actually, there's 3 of those. And I look, is when it combines with silver an exception, and I find silver on my exception side. So that means it is now insoluble. So it's the opposite of whatever column it's in. So since we're in the soluble column, when it combines with silver, it is therefore insoluble, and it would precipitate out. We'd see a solid form in our solution, so I'd put an S for solid. S doesn't stand for soluble, it stands for solid, which means it's an insoluble product. You should also be able to complete a double replacement reaction to actually get our products here. And so in order to do that, When we place these substances in solution, they're going to form ions, and that's why they were electrolytes. So Na and Cl separate into Na plus and Cl minus, and then the Ag plus and NO3 minus. A double replacement means that this metal now hooks up with this nonmetal, and then this metal is going to hook up with this nonmetal. So they switch partners. So it's two different replacements. But when you form your products, we don't simply just put them together. We have to do our drop and swap of our charges. In this case, it's very simple because they are just 1-to-1. So we put a 1 here and a 1 here, and simply write NaNO3. And the same thing, Ag plus and Cl minus. It's a 1-to-1 ratio. So what we do is they ask you to complete this reaction, and they gave you only the reactants. You'd first do the double replacement. You do your drop and swap, looking up the oxidation states first, and then you go to table F and determine if any substance is going to form the insoluble, or we say precipitate. So example, complete the following double replacement reaction and determine the insoluble product. So we would do that. We'd see that this is aqueous, as we did earlier, and this is solid, and then say this is going to be the precipitate. In terms of solubility, like dissolves like. So going back to our bonding unit, a polar molecule is going to dissolve in another polar substance, and a nonpolar dissolves in nonpolar. And so that's the reason why oil and water do not mix, because water is very polar and oil is nonpolar, and therefore they are not like substances. What factors affect the solubility, the ability of something to dissolve? Well, we can increase solubility if we increase the temperature for solids. So as we increase the temperature of our solution, we can dissolve more of our solids. If we decrease the temperature, we can dissolve more gases, so they're opposite. And if we, looking at gases again, if we increase the pressure, we can increase the solubility. For example, here you can see as I increase the pressure, I'm pushing more particles into solution. We could also speed up the dissolving. So we're not going to be able to dissolve more, but we could speed it up. And we can do that by stirring, so we can have more particles interacting with each other. Or we can increase the surface area. So if we have something that has low surface area compared to high surface area, that means we have more sides to interact with, and therefore it would dissolve faster. In terms of the types of solutions that we can make an unsaturated solution where it is not quote-unquote full. We can dissolve more particles. A saturated solution where no more of our solute particles will dissolve. So if I added any more, it would simply just fall to the bottom. It would not dissolve. And a supersaturated solution we can make by heating a solution and then in turn cooling it down. So essentially we're going to get more solute to dissolve than it can normally dissolve. And this is very unstable, and we can actually form crystals. And this is how things like rock candy are formed. Because it's unstable, any kind of agitation will cause it to precipitate out. So looking at table G, here's just one saturation curve, but we have many on table G. If you are on the line, you've created a saturated substance, meaning if I, in this case, at 40 degrees Celsius, if I add approximately 64 grams of KNO3, I make a saturated solution. Anything less than that, under the line, is unsaturated, and then over the line would be supersaturated. So the only way that I can get 90 grams to dissolve of KNO3 would be to first heat this, dissolve the substance, KNO3 in water, and then cool it back down to 40 Celsius. And therefore I can get this 90 grams to have been dissolved in there. Again, it's unstable, and it will very easily precipitate out. So here's an example of a solubility curve question. If you dissolve 50 grams of NaNO3 at 30 Celsius, what type of solution did you make? So first find NaNO3. And on the regions, I would highlight the line or like trace it so you know that it's the correct line, because they get kind of jumbled up here. So here's NaNO3 right here. I always start with temperature, so 30 degrees Celsius. And I'm going to go up to my line. So I could dissolve about, let's say, 95 or 96 grams of NaNO3 in 100 grams of water. That would be saturated. If I'm only putting 50 grams, so again at 30 degrees Celsius, 50 grams is here, it's well under the line here. So if we're under the line, it's an unsaturated solution. Let's see another example. According to table G, what is the maximum amount of KNO3 that can be dissolved in 100 grams of water at 60 degrees Celsius? So start off with 60 degrees Celsius. What's the maximum amount? That's going to be my saturated solution. So I'm going to go up to the line, NaNO3, and the maximum amount I could dissolve is approximately, let's say, 127. So I can dissolve 127 grams of sodium nitrate in 100 grams of water at 60 Celsius. All right, let's look at another example. What is the amount of sodium nitrate that can be dissolved in 50 grams of water at 80 Celsius? So we are changing the amount of water from 100 grams to 50 grams. But let's first just solve this for what the chart is intended for, 100 grams of water. So I take 80 Celsius, I'm going to go up to NaNO3, go across, and let's say it's 146 grams. So in 100 grams of water, I could dissolve 146 grams of NaNO3. So now, if I want to use 50 grams of water, that's half the amount of solvent. If you have half the amount of solvent, I have half the amount of space to dissolve in. I can only dissolve half the amount of solute. So 146 divided by 2 gives me 73 grams. So I can only dissolve 73 grams. Sometimes, instead of 50 grams of water, they'll say 200 grams of water. And in that case, you would then double the amount, not half it. And lastly, we're going to go through calculations of concentration. So we can use table T. This is a parts per million question. You would know it's a parts per million question because you'll see ppm, or we'll say parts per million. So a sample of water is found to contain 0.010 grams of lead in 15 grams of solution. What is the concentration in parts per million? So here's the formula from table T. The mass of the solute is what you're dissolving, and then obviously the solution is the whole thing. So the solution is 15 grams, it goes on the bottom. The solute, the lead that's dissolved in there, is the 0.010 grams. That goes on top. And then don't forget times a million. It's 1 and 6 zeros. Always make sure that you've done that correctly. So I always suggest plugging into your calculator twice. So this divided by this times a million gives me 670 parts per million, ppm. Molarity is another way to look at concentration. And the formula is big M, molarity, equals moles of solute over liters of solution. Make sure that it's liters. So an example of a question would be, a solution has a volume of 2.5 liters and contains 0.70 moles of sodium chloride. What is the molarity? So I'm solving for big M. I plug in my mole value here, my liters here, and I get an answer of 0.28 big M, so 0.28 molar. So the bigger this number is, the more concentrated a solution is, the more solute that's dissolved. And let's look at solutions versus pure water. We talked about why we add salt to our roadways in the winter, and its effect and why that occurs. So solutions have a higher boiling point and a lower freezing point than pure water. So we have boiling point elevation and freezing point depression when we add ionic compounds, salts, to water. So ionic compounds, these salts, have the greatest effect on increasing the boiling point and decreasing the freezing point. And the reason why is they produce a lot more particles when dissolved in solution because they break apart into ions. So the more particles that we form, the greater the effect. So if I took pure water and then I added a molecular, a covalent substance, then this is not going to break apart. So I put one particle in, I get one particle essentially out. And so this is not going to have a great effect on changing the boiling point or freezing point. If I add an ionic compound like salt, NaCl, it's going to break apart into Na plus and Cl minus. That's two particles. That's going to increase the boiling point and decrease the freezing point. If I use a substance like this, Na2CO3, it's going to break apart into Na plus and CO3 minus, but I have two Na pluses here, so it's actually 3 particles. And so the more particles, the greater the effect on melting point and boiling point. So the boiling point is going to go up, and the melting point or freezing point goes down. So when we add ice melt is calcium chloride, CaCl2, gives us 3 particles, just like this situation here, and that's a much better substance to put on our walkways, for example, to melt ice than NaCl, and especially better than putting something like this or like glucose, for example. So here's an example. Which compound, when dissolved in water, will have the highest boiling point? Or we could say lowest freezing point. And so you first figure out who's ionic. So this is ionic, this is ionic, this is covalent, all nonmetals, so that's out. And this is ionic. And then you want to figure out who dissociates into the most amount of particles or ions. So CaCl2, I get 1 of these and 2 of these. That's 3 particles, and so that's my answer. NaCl and NaI only dissociate into 2 particles. They don't have as much of an effect.